Tonight, we embark on a journey, a quiet exploration across the vast, silent stretches of our solar system to uncover the peculiar and the profoundly beautiful among its many moons. While the grand planets often capture our imagination, dominating textbooks and the aspirations of space agencies, there exist smaller, less celebrated worlds, each holding secrets just as compelling, just as intricate, as their more famous planetary companions. So, before you get comfortable, take a moment to like the video and subscribe. Let me know in the comments where you are in the world and what time it is for you. We'll be focusing our gaze, with a gentle, unhurried pace, upon a selection of these celestial bodies, beginning with a quartet intimately bound to Jupiter, known collectively as the Galilean moons. These four worlds, though orbiting in relatively close proximity to one another, are, in their very essence, astonishingly diverse. Imagine, if you will, a moon perpetually consumed by volcanic fury, spewing molten rock and sulfur into its thin atmosphere. Then, picture a sibling world, shimmering with an icy shell, beneath which scientists now believe a vast, liquid ocean harbors one of the solar system's most promising chances for extraterrestrial life. Next, we'll drift towards the largest moon in our entire solar system, a colossal sphere that dwarfs even a planet, carrying within its depths a mystery that has puzzled astronomers for decades. And finally, our journey will conclude with an ancient, deeply scarred moon whose pristine, heavily cratered surface offers a pristine, undisturbed record stretching back to the very dawn of our solar system's tumultuous formation. In this video, we will embark upon a deep, unhurried exploration of these extraordinary worlds, meticulously examining each one, delving into the very essence of what renders them so profoundly unique. By the conclusion of our shared journey, I trust you will possess a profound understanding of why these moons have become the focal point, the coveted subjects, of two major space missions slated for this very decade, originating from both NASA and the European Space Agency, known as ESA. Our cosmic voyage commences, appropriately, with the innermost of these four giants Io. Let us gently ease into understanding the intricate context of O, familiarizing ourselves with its place in the grand, swirling tapestry of the Jovian system. Jupiter, the colossal gas giant, is orbited by a staggering number of celestial companions. To date, we have identified and cataloged no fewer than 79 moons dancing in its gravitational embrace, each a silent witness to the planet's majestic spin. Among this multitude, a distinct hierarchy emerges. A handful of smaller, more intimate moons trace their paths in close proximity to the planet itself, some even weaving their way through the delicate, ethereal strands of Jupiter's rings, almost hidden within that cosmic halo. Beyond this inner circle, we encounter the quartet that forms the heart of our present discussion, the four magnificent Galilean moons. These celestial bodies bear the esteemed name of Galileo, the brilliant astronomer who, in the year 1610, first turned his rudimentary yet revolutionary telescope towards the heavens, and, in doing so, unveiled these distant lights, forever altering our perception of the cosmos. Arranged in ascending order of their distance from Jupiter, from the closest to the furthest, these remarkable siblings are O, Europa, Ganymede, and Callisto. Further still, sprawling across the outer reaches of the Jovian domain, lie what are known as the irregular moons of Jupiter, a collection of smaller, more distant wanderers, each following its own elongated and often eccentric trajectory, far, far removed from the more orderly dance of the inner system. Io, our initial focus, clings remarkably close to its immense parent planet. Its orbital path carries it a mere 350 kilometers above Jupiter's tumultuous cloud tops. To put that into a tangible perspective, if you were to stand upon the rugged, sulfur-rich surface of O, gazing upwards into its alien sky, Jupiter would loom as an unimaginably gargantuan presence, appearing an astonishing 39 times larger than our own familiar moon does to us from Earth. Imagine that colossal orb, painted in swirling bands of ochre and cream, dominating the entire celestial dome, a breathtaking and somewhat overwhelming spectacle. This intimate proximity also dictates Io's incredibly swift orbital dance. It completes a full circuit around Jupiter in a mere 40.5 hours, a fleeting passage compared to the leisurely month-long journey of Earth's moon. This rapid, close embrace has profound consequences for Io, most notably in the form of immense tidal forces. At certain junctures within its orbit, the gravitational pull of Jupiter tugs and stretches Io with such intensity that its very surface is thought to bulge outwards, forming a colossal tidal deformation that can reach heights of up to 100 meters. To draw a parallel, consider the gentle ebb and flow of our Earth's oceans, the rhythmic rise and fall of the tides, a phenomenon primarily orchestrated by the gravitational influence of our own moon. On Earth, this effect is, comparatively speaking, quite subtle. Our ocean tides typically shift by only about 2 meters between their high and low points. Now, scale that up dramatically. Due to its exceptionally close proximity to the most massive planet in our solar system, experiences a tidal force that is a staggering 300% more potent than the one our moon exerts on Earth. This constant, immense gravitational needing, intensified by the additional tugs from Jupiter's other large moons, particularly Europa and Ganymede, prevents Io's orbit from ever settling into a perfectly circular, serene path. Its orbit remains perpetually eccentric, a slightly elongated ellipse, ensuring that Io never truly finds a moment of respite from these ceaseless, internal stresses. Furthermore, Io is locked in a state of synchronous rotation with Jupiter, a phenomenon known as tidal locking. This means that a single day on Io is precisely the same length as its orbital period around Jupiter. Consequently, just as we on Earth are forever presented with the same familiar face of our moon, so too does Io perpetually present only one of its hemispheres to the magnificent, swirling visage of Jupiter. The other side remains a hidden, silent realm, always facing away from the planetary behemoth. Despite being the second smallest among the 4 Galilean moons, Io is, in its own right, a significantly sized celestial body. Its diameter is quite comparable to that of Earth's moon, and it shares a similar overall density. This likeness in density suggests that Io possesses a gravitational pull roughly equivalent to that of our own moon. However, delving deeper into its characteristics, we uncover yet another intriguing distinction. Io boasts the highest density of any moon in the entire solar system. This particular attribute is just one of its many remarkable, unique features. Another striking difference lies in its fundamental composition. Unlike the majority of other large moons found across our solar system, which are primarily constructed from a blend of water ice and silicates, Io is predominantly composed of silicate rock and iron. This makes it far more akin to the terrestrial planets, such as Earth, Mars, and Venus, and indeed, to our own moon. In fact, Io holds the rather astonishing record for possessing the least amount of water of any known body in our solar system. Its parched interior is believed to harbor a core primarily fashioned from iron, or perhaps a mixture of iron sulfides, nestled beneath a thick mantle and a crust rich in silicates. Intriguingly, this core is not thought to be convecting, meaning there are no large, scale movements of molten material within it. This inference is drawn from the notable absence of any detectable magnetosphere enveloping the moon, a magnetic field typically generated by the churning of electrically conductive material in a planet's or moon's core. However, the mantle, situated just beneath the crust, is believed to exist in a liquid state, extending to a depth of at least 50 kilometers. It is from this fiery, subsurface ocean of molten rock that the moon's extraordinary volcanism originates, leading us to perhaps the most captivating and defining aspect of Io, the hundreds upon hundreds of enormous, active volcanoes that ceaselessly erupt across its entire surface. Before the dawning of the 1970s, our knowledge of Io was, to be quite frank, remarkably sparse. Early telescopic observations had begun to offer tantalizing hints, suggesting a world utterly devoid of water and perhaps cloaked in a surface of sulfur. But these were largely educated guesses, shrouded in the limitations of distant viewing. The very first robotic mission to afford us any kind of detailed glimpse of Io was Pioneer 11, which made its flyby in the year 1974. While the images and data it transmitted back to Earth were, by today's standards, still somewhat crude and indistinct, Pioneer 11 nonetheless made a crucial discovery. It confirmed that Io was indeed primarily composed of silicate rock rather than the expected water ice, and that it possessed a tenuous, wispy atmosphere. Pioneer 10, an earlier mission, had also been intended to capture close-up images of Io, but unfortunately, this endeavor was thwarted. Jupiter's incredibly intense radiation belts interfered catastrophically with the spacecraft's onboard command system, rendering it unable to execute the imaging sequence. The radiation dose that Pioneer 10 encountered near Jupiter was an astonishing 10,000 times stronger than the maximum radiation levels found around Earth, a stark testament to the formidable environment surrounding the gas giant. The true unveiling of Io, however, came with the subsequent Voyager missions. In 1979, Voyager 1, followed by its twin Voyager 2, executed remarkable flybys of the Jovian system. Voyager 1, in particular, swooped past Io at an incredibly close distance of only 20,000 kilometers, allowing it to capture breathtaking, unprecedented close-up images of Io's tortured, vibrant surface. What these images revealed was a truly astonishing landscape, a riot of vivid, almost painterly colors, and, perhaps most strikingly, a complete and utter absence of impact craters, a stark contrast to nearly every other solid body in the solar system. Instead of craters, Voyager 1 discovered towering mountains, some of which soared higher than Earth's Mount Everest, alongside vast volcanic pits, hundreds of kilometers wide, and what appeared to be extensive, solidified lava flows snaking across the plains. But the most profound and game-changing discovery was the unmistakable presence of colossal plumes, erupting majestically from the surface itself. This incontrovertible evidence proved, beyond any doubt, that Io is volcanically active, a world in a constant state of fiery upheaval. To this day, Io remains the first and indeed the only place in our solar system, apart from Earth, where active, visible volcanism has been directly observed, excluding the more subtle cryovolcanoes found on some icy moons. Voyager 1 also definitively confirmed that Io's spectacular, multi-hued surface is largely cloaked in various sulfur frosts and compounds. It is this rich tapestry of sulfur, oxidized and transformed by the intense radiation and volcanic heat, that bestows upon Io its incredible spectrum of colors, from vibrant yellows and oranges to deep reds, and even stark whites. The mission also found that these sulfur compounds are the dominant constituents of Io's thin, transient atmosphere. Voyager 2, following in its sibling's wake, observed Io in July of that same year, 1979. Though it passed at a greater distance, approximately 1 million kilometers, it still managed to detect 7 of the 9 volcanic plumes that Voyager 1 had witnessed just 4 months prior in March. This observation provided crucial evidence that these specific volcanoes had remained continuously active throughout that 4-month interval, a testament to Io's relentless geological dynamism. However, the truly extraordinary, highest-resolution images and the most detailed insights into Io arrived with the Galileo spacecraft, which entered orbit around Jupiter in 1995. While Galileo wasn't specifically designed with Io as its primary target, its extended mission in the Jovian system allowed it to execute multiple close flybys, acquiring some of the most incredibly detailed images we possess of Io's surface to this very day. Regrettably, the Galileo spacecraft never operated at its full, intended capacity due to a series of mechanical malfunctions with its main antenna, which meant that had it been fully operational, we might have received even more spectacular and comprehensive data. Despite these limitations, Galileo was able to capture stunning views of numerous active plumes erupting from Io's volcanoes. It further confirmed that these volcanoes were indeed spewing sulfur and silicate magmas, remarkably similar in composition to the molten rock found deep within Earth. With one notable distinction, the magma on Io is also exceptionally rich in magnesium. The surface of Io, as revealed by these missions, is a truly spectacular canvas of color. The expansive yellow plains, stretching across vast regions, are primarily composed of pure sulfur. Interspersed among these, we find brilliant white areas, which are understood to be fresh deposits of sulfur dioxide frosts, recently solidified from volcanic gases. As we look towards the polar regions of the Moon, a subtle shift in coloration becomes apparent. The sulfur there appears redder than the rest of the planet. This reddish hue is attributed to radiation damage inflicted by the relentless bombardment of high-energy particles emanating from Jupiter's powerful magnetosphere. In other areas, particularly where volcanic activity has been most vigorous, deep reds and oranges paint the landscape. These are the striking deposits left behind by the colossal volcanic plumes that have soared hundreds of kilometers above Io's surface, raining down their fiery debris over vast expanses. One of the most visually arresting of these deposits originates from a volcano named Pell. Sadly, Pale was largely inactive during Galileo's tenure around Jupiter. However, Voyager 1, during its earlier flyby, was fortunate enough to witness a truly massive plume erupting from Pale. In the iconic image captured by Voyager 1, this plume is seen reaching an astounding height of 300 kilometers, while simultaneously spreading out to an incredible width of 200 kilometers. To put that scale into perspective, that single volcanic plume was roughly the size of the entire state of Alaska. Interestingly, the typical sources of lava flows on Earth are usually the caldera-like depressions, the vast, bowl-shaped craters normally found at the summits of volcanoes. However, on Io, these characteristic depressions are not typically situated on high peaks. Instead, we observe expansive lava lakes, often encircled by towering, steep walls. Consider Loki Patera, for instance, which is the largest volcanic depression on Io, a truly immense feature spanning 200 kilometers in diameter. These vast lakes are understood to be directly connected to deep, subterranean reservoirs of molten lava, though they typically present a thin, solidified crust across their surface. On average, Loki Patera alone accounts for approximately 25% of Io's total heat output. But periodically, this thin crust on the lava lake will dramatically sink back into the molten depths below, causing Loki to unleash a surge of heat, sometimes producing 10 times its normal output. This dramatic crustal collapse has been vividly captured in observations of one of Io's other major volcanoes, Tvashtar Patera. Normally, this area exhibits a particular appearance, but in striking images, the crust can be seen in the very act of falling into the molten lake. In one particularly intense image, where the entire region is rendered in stark white, the radiant energy emanating from a lava curtain, a sheet of incandescent molten rock erupting from a fissure, was so extraordinarily intense that the camera could only register pure white, completely saturated by the sheer brilliance of the eruption. In 2007, the New Horizons spacecraft, on its epic voyage to Pluto, utilized Jupiter as a crucial gravity assist maneuver, slingshotting around the gas giant to gain momentum for its onward journey. During this brief but invaluable flyby, New Horizons seized the opportunity to test and calibrate its sophisticated equipment. It focused its powerful lenses on Io, and what it captured was nothing short of astonishing. Tivashtar Padare, the volcano we just mentioned, was observed in a state of full, spectacular eruption, its colossal plume soaring hundreds of kilometers above Io's surface. The images also revealed numerous smaller eruptions dotting the moon's surface, a testament to its pervasive volcanic activity. It must be admitted, to witness such raw, planetary power captured from so vast a distance is truly one of the most impressive spectacles space exploration has ever afforded us. While Io's volcanoes tend to be relatively flat, its surface is also home to some incredibly tall mountains, defying the typical volcanic topography. The highest of these majestic peaks reaches an astounding 18 kilometers in height, dwarfing even the most formidable mountains on Earth. These mountains often stand in splendid isolation, not forming part of extensive ridges or mountain ranges. Although most of them are not themselves volcanoes, the presence of lava lakes in their vicinity strongly suggests the existence of faults and fissures in the crust near these colossal structures, indicating ongoing geological stress and activity. Another profoundly unique aspect of Io is its intricate and dynamic interaction with Jupiter's immensely powerful magnetic field. Jupiter possesses an extraordinarily vast and potent magnetosphere, a colossal bubble of magnetic force that extends millions of kilometers into space. Io orbits deep within some of the strongest sections of this magnetic field, a region of intense plasma and energetic particles. The unusual nature of this interaction becomes apparent when particles from Io's thin, tenuous atmosphere, or those ejected during its volcanic eruptions, are lost to space. These freed particles do not simply dissipate. Instead, they become trapped, forming a diffuse, ethereal, neutral cloud that orbits Jupiter, stretching far beyond and behind Io's own orbital path. But this is only half the story. Encircling Jupiter and encompassing Io's orbit is another distinct feature known as the plasma torus. Imagine a giant, glowing donut composed of ionized particles, which rotates in perfect synchronization with Jupiter's magnetic field. This plasma torus spins at an astonishing velocity, approximately 70 kilometers per second, a speed far greater than Io's own orbital velocity of 17 kilometers per second. Io, in its relentless orbit, plunges directly through the very heart of this rapidly spinning plasma torus. As it does so, the energetic particles within the torus relentlessly bombard the more quiescent particles in Io's neutral cloud, exciting them to higher energy states. These newly ionized particles are then swept up by Jupiter's magnetic field lines, feeding directly into the plasma torus. This process, a continuous exchange of matter and energy, results in a staggering loss rate of approximately 1 ton of material per second from Io's neutral cloud into the plasma torus, significantly increasing the overall size and density of Jupiter's magnetosphere. In fact, if Jupiter's magnetosphere were visible to the naked eye, it would appear in our sky to be roughly the same colossal size as our own full moon. Io's profound interaction with Jupiter extends even further. The magnetic field lines of Jupiter, which Io constantly traverses, create a direct electromagnetic link between Io's atmosphere and neutral cloud and Jupiter's polar upper atmosphere. This connection generates a powerful electric current, a cosmic conduit known as the Io flux tube. A flux tube is essentially a concentrated bundle of magnetic field lines. We see similar phenomena on the Sun, where flux tubes connect sunspots, made brilliantly visible by the charged plasma flowing along them. In Jupiter's case, Io's flux tube manifests as a spectacular aurora trail around Jupiter's poles. If you could observe it, you would see a distinct, luminous footprint, where the flux tube, originating from Io, strikes Jupiter's upper atmosphere, igniting a brilliant display of light. Auroras are also visible on Io itself, though they are not confined solely to its poles. These incandescent displays, shimmering in various hues, represent different particles in Io's atmosphere being ionized. Green light indicates the presence of sodium, red signifies excited oxygen, and a captivating blue glow points to sulfur. Each color, a silent testament to the moon's fiery internal life and its dynamic interaction with its colossal parent. Let us now gently drift our attention away from the volcanic inferno of Io and towards a world of crystalline ice and profound mystery Europa. This moon, the second of Jupiter's Galilean satellites, is arguably one of the most exciting and enigmatic objects in our entire solar system. It is a world of breathtaking beauty, brimming with puzzles that scientists are only just beginning to unravel. Our first close-up image of Europa, a grainy but historic photograph, was captured by the Pioneer probe way back in 1973. Since that initial glimpse, subsequent missions, notably the Voyager spacecraft in 1979 and the Galileo probe, which orbited Jupiter from 1995 to 2003, have provided increasingly detailed views of this captivating moon. With each successive visit, Europa has never failed to surprise us, deepening its allure and intensifying our scientific curiosity. While many of Europa's fundamental puzzles remain tantalizingly unsolved, we are steadily, patiently, piecing together a more coherent understanding of this icy realm. First, let's establish Europa's position within the vast architecture of the Jovian system. Europa is the second moon out from Jupiter among the four Galilean giants. It is also the smallest of this quartet. However, do not let its relative size within the Galilean family mislead you. Europa is still the sixth largest moon in the entire solar system, a truly substantial body, only slightly smaller than Earth's own moon. Its diameter measures approximately 3,000 kilometers across. Europa completes one full orbit around Jupiter in a relatively swift 3.5 Earth days, a testament to its still close proximity to the gas giant, an intriguing aspect of the first three Galilean moons. Europa and Ganymede, is their intricate orbital dance, locked in a precise gravitational ballet known as a 402:1 orbital resonance. This means that for every single orbit Ganymede completes around Jupiter, Europa will complete exactly 2 orbits, and Io will complete precisely 4 orbits. This highly stable and mathematically elegant configuration is not a mere coincidence. It is a direct consequence of their mutual gravitational influences, a delicate cosmic tug of war that keeps their orbits locked in this rhythmic pattern. This orbital resonance, coupled with the constant gravitational tugging from its larger siblings and Jupiter itself, prevents Europa's orbit from ever becoming perfectly circular. Instead, it maintains a slight, persistent eccentricity, meaning it is not a perfect circle, but a slightly elongated ellipse. Due to this subtle elliptical path, the magnitude of Jupiter's gravitational force acting upon Europa constantly fluctuates, increasing when Europa is closer to Jupiter and decreasing when it is further away. This continuous stretching and compressing of Europa's interior generates immense tidal forces, which in turn produce significant internal heating. These forces are not merely academic. They have a profound influence on the moon's surface appearance and, crucially, on the dynamic processes occurring deep beneath its icy shell. Europa's surface is predominantly composed of water ice, a pristine, white canvas that reflects sunlight with remarkable efficiency. As you observe images of Europa, its appearance is immediately striking and remarkably distinctive, characterized by an intricate network of long, continuous fractures and cracks crisscrossing its entire globe. These enigmatic features are known as lineae, a Latin term simply meaning lines. These lineae are often quite narrow, typically only about 1 to 2 kilometers wide, but they can extend for thousands of kilometers, snaking across Europa's vast icy expanse, creating a truly global pattern. The precise mechanisms by which these lineae form remain a subject of active scientific debate and ongoing research. At present, the most widely accepted and likely theory posits that as Europa's icy crust is stretched and pulled apart by the relentless tidal flexing, warmer, more pliable material from the subsurface ocean or a slushy layer beneath it wells up to fill the resulting gaps. This process is thought to be analogous to the formation of mid-ocean ridges on Earth, where new crustal material emerges from the mantle as tectonic plates pull apart. In some images, particularly those captured by the Galileo spacecraft, you might notice small, dark brown spots scattered across Europa's surface. These features are quite small, typically only about 10 kilometers across, and are known as lenticula, meaning freckles in Latin. Lenticulae are also believed to be formed by the upwelling of hot, less dense material from beneath the icy crust. This warmer material either pushes the existing crust upwards, creating dome-like structures, or, in more dramatic instances, completely breaks through the surface, creating chaotic patches. Should the underground material have indeed breached the surface, what we then observe are these utterly strange and unusual terrains, appropriately termed chaos terrains. These are incredibly rough, jumbled patches of ice, often surrounded by what appears to be a much smoother, undisturbed surface. Scientists believe these chaos terrains are areas where the icy crust has been thoroughly fragmented and churned, perhaps indicating regions where the subsurface ocean is particularly close to the surface, or where significant heat flow has occurred. These spots are expected to be relatively soft in geological terms and are believed to contain significant information about the composition and dynamics of what lies hidden beneath Europa's enigmatic surface, a topic we will delve into more deeply later in our discussion. Data transmitted from the Galileo mission also offered tantalizing suggestions that Europa's equatorial regions might be adorned with icy spikes, towering formations known as penitentes. These striking vertical blades of ice are hypothesized to reach heights of up to 15 meters and are believed to form from the direct, intense overhead sunlight striking the equator, causing the ice to sublimate in a patterned way, leaving these sharp, blade-like structures behind. Interestingly, penitentes are also found on Earth, specifically in arid, high-altitude regions, though nowhere near the colossal scale observed on Europa. Despite being roughly the same age as the entire solar system, Europa's surface presents a remarkably pristine appearance, almost entirely devoid of impact craters. Europa boasts fewer than 50 major craters, a stark contrast to Earth's moon, for example, which is pockmarked with more than 5 Zalozan craters exceeding 25 kilometers in diameter. This dramatic difference is a strong indicator that Europa's surface is in a constant state of dynamic change and active reformation. Geological models suggest that Europa's surface is exceptionally young in geological terms, estimated to be only about 30 to 180 million years old, a mere blink in the vast timescale of the solar system. Furthermore, Europa's icy surface holds another remarkable distinction. It is the smoothest surface of any known solid celestial object in the entire solar system. Its pristine, icy crust also possesses an exceptionally high albedo, or light reflectivity, measuring approximately 0.64. This means that Europa reflects 64% of the sunlight that strikes it, rendering it one of the brightest objects in the outer solar system. To put it simply, Europa's albedo makes it a staggering 5 times brighter than our own moon, gleaming brilliantly against the dark backdrop of space. However, this bright, smooth surface is not a tranquil haven. Europa is constantly bombarded by an intense and ceaseless blast of radiation emanating from Jupiter's powerful magnetosphere. The radiation level at Europa's surface is truly formidable, equivalent to a dose of approximately 400 millisieverts per day. To understand the severity of this, exposure to radiation at that sustained level would be more than sufficient to prove fatal to a human being within a single day. This relentless radiation bath plays a crucial role in shaping Europa's surface chemistry and appearance. The subtle reddish, brown coloration that is often observed spread across the cracks and fractures of the Moon's icy shell is believed to be the result of various salt and sulfur compounds, intrinsically mixed with the water ice, which are then chemically modified and darkened by the intense, ionizing radiation from Jupiter. A recent study, conducted by scientists at NASA's Jet Propulsion Laboratory, JPL, has even put forth the intriguing hypothesis that Europa might possess the astonishing ability to glow in the dark. The theory suggests that the energetic ions from Jupiter's radiation belts penetrate Europa's icy surface, energizing the molecules beneath. As these excited molecules return to a lower energy state, they would release this stored energy in the form of visible light, causing the Moon to emit a faint, ethereal glow. Unfortunately, we are unable to directly observe Europa's dark side from Earth, as our position relative to the Sun always means we are observing its illuminated face. Therefore, we must patiently await future dedicated missions to Europa before we can definitively prove or disprove this captivating possibility. The radiation received from Jupiter also plays a significant and dynamic role in shaping Europa's incredibly tenuous atmosphere, or exosphere. Europa possesses an extremely thin, wispy atmosphere composed primarily of oxygen. However, unlike the oxygen-rich atmosphere of Earth, which is largely a product of biological processes, photosynthesis, the oxygen on Europa is formed through a process called radiolysis. In simple terms, radiolysis is the process by which Jupiter's intense radiation relentlessly bombards Europa's water-ice surface, causing the H2O molecules to split apart into their constituent atoms oxygen and hydrogen. The hydrogen, being an exceedingly light gas, largely escapes Europa's comparatively weak gravity altogether, dissipating into space. However, a significant portion of the heavier molecular oxygen is retained, forming the Moon's thin atmosphere. Both the escaping hydrogen and the retained oxygen, after detaching from Europa, form a dispersed neutral cloud that subtly follows Europa's orbit around Jupiter. In essence, Europa is slowly, continuously shedding its own substance into the Jovian system. In a truly groundbreaking discovery, in 2012, the Hubble Space Telescope provided direct observational evidence of plumes of water vapor erupting from Europa's south pole. The images suggested that these magnificent plumes of water could rise to altitudes of up to 200 kilometers above the Moon's surface, a truly astonishing display of cryovolcanism. This discovery immediately amplified Europa's allure as a potential abode for life. Further corroborating evidence for water plume activity on Europa emerged in 2018 when astronomers re-examined old data from the Galileo mission using new, sophisticated data analysis techniques, revealing additional indicators of these powerful geysers. A dedicated mission specifically designed to study these plumes would offer an invaluable opportunity to understand what lies beneath Europa's solid ice surface, potentially allowing us to sample the subsurface ocean without the enormous engineering challenge and expense of actually landing on the Moon and drilling through its thick icy crust. Because what may lie hidden, shielded beneath that formidable solid ice surface, is perhaps the single most fascinating and tantalizing aspect of Europa. Scientists now believe, with a high degree of confidence, that a vast, global ocean of liquid water exists, trapped between Europa's rocky mantle and its overlying water ice crust. The very first clues pointing to the existence of this astounding ocean world, concealed beneath its icy shell, were provided by the Voyager probes in 1979 and more conclusively by the Galileo probe in the late 1990s. During the period between these missions, a significant and measurable change was detected in Europa's magnetic field. Such a shift would be impossible to explain unless there existed a substantial layer of electrically conductive fluid, like a salty ocean, circulating beneath its surface. Further evidence for this subterranean ocean comes from Europa's icy crust itself. Observations indicate that Europa's crust rotates at an angle of approximately 80 degrees relative to its interior, a phenomenon that would be utterly impossible if the icy crust and the rocky mantle were rigidly and mechanically coupled. Instead, this differential rotation strongly suggests that the icy crust effectively floats upon a global ocean of liquid water. Scientists estimate that this icy shell makes one complete rotation around the Moon once every approximately 12,000 years, a truly glacial pace of movement. The very existence of this unattached, floating icy crust also helps to explain the multitude and seemingly chaotic distribution of the lineae, those long cracks and fractures on Europa's surface. If the crust were rigidly connected to the mantle, tidal flexing would cause lineae to form at very specific, predictable points on Europa's surface, following distinct stress patterns. However, because the position of the crust relative to the underlying ocean changes over immense timescales, and no single spot on the crust remains in the same tidal stress field for long, more and more lineae are continuously generated across the entire surface, creating the intricate, global network we observe. Europa orbits at an immense distance of approximately 780 million kilometers from the Sun, a staggering 5 times further away than our own Earth. This colossal separation means that the sunlight reaching Europa, or indeed any other moon in the Jovian system, is incredibly faint, roughly 25 times weaker than what we experience on Earth. Consequently, and perhaps unsurprisingly, it is extraordinarily cold in this distant realm of the solar system, so cold, in fact, that Europa's surface remains perpetually frozen solid. The average surface temperature on Europa hovers around a frigid 160 degrees Celsius at the equator, plummeting even further to a bone-chilling 220 degrees Celsius at the poles, temperatures so low that Europa's icy crust is as hard and unyielding as granite. However, the relentless tidal pressures exerted on the Moon as it orbits Jupiter generate substantial internal heat, keeping Europa's core warm. This geothermal activity, originating from the core, is believed to be sufficient to maintain the subsurface ocean in a liquid state, preventing it from freezing solid despite the extreme surface temperatures. This ocean is thought to lie beneath a relatively modest layer of solid, frozen crust, estimated to be only about 15 to 25 kilometers thick. The ocean itself is believed to be remarkably deep, probably ranging from 60 to 150 kilometers in depth. Intriguingly, despite Europa being only about 1/4 the diameter of Earth, its subsurface ocean may contain an astonishing amount of water, potentially twice as much as all of Earth's oceans combined. This immense volume of water, trapped beneath the ice, is a significant factor in Europa's scientific appeal. What truly elevates the scientific interest in Europa's ocean is the strong belief among scientists that it is in direct contact with Europa's silicate rocky mantle, the seafloor of this alien world. This direct interaction is crucial because it makes Europa's ocean a potentially suitable environment for life as we currently understand it. We believe that life, at its most fundamental level, requires 3 essential ingredients to form and thrive: liquid water, a source of minerals, and a source of energy. From the compelling evidence gathered so far, Europa appears to possess all of these critical requirements. Scientists are exceptionally confident that this ocean not only exists, but that active chemical reactions can take place within its depths. Furthermore, there is believed to be ample tidal energy heating the core, suggesting that geothermal activity, similar to the hydrothermal vents found on Earth's ocean floors, may exist on Europa's seafloor. As we have seen on Earth, entire ecosystems, teeming with unique forms of life, can flourish in such deep sea environments, far removed from the sun's light, deriving their energy from chemosynthesis rather than photosynthesis. Therefore, For now, Europa stands as one of the most promising and likely places where we might one day discover life beyond Earth. With this profound potential in mind, NASA's Europa Clipper spacecraft is a highly anticipated mission, initially scheduled to launch in 2022, though its launch window has since been updated to late 2024. It is expected to reach the Jovian system and begin its detailed study of Europa by the end of this decade. This ambitious mission is designed to perform more than 42 close flybys of Europa, meticulously gathering data on its ocean, surface, and potential for habitability. The European Space Agency ESA is also actively developing its own spacecraft, known as JUICE, an acronym for Jupiter Icy Moons Explorer. JUICE is also scheduled for a 2022 launch, with an expected arrival in the Jovian system by 2030. This mission will embark on a comprehensive exploration of Jupiter and three of its largest icy moons, Ganymede, Callisto, and Europa. Both the Europa Clipper and JUICE probes are specifically equipped and designed to thoroughly examine Europa's enigmatic water plumes and its tenuous atmosphere, providing invaluable insights. NASA is also contemplating a follow-up mission, a Europa lander, which would attempt to touch down on the moon's surface to conduct in situ investigations. But this mission is planned for well after the Europa Clipper has completed its initial survey. These upcoming missions represent a monumental leap forward in our understanding of Europa. They will undoubtedly help us to learn significantly more about this captivating moon and, critically, to hopefully confirm the answer to the most tantalizing question of all: does it, or can it, sustain life? At the very least, these missions will offer us a fresh and profound perspective on our solar system, deepening our comprehension of its intricate workings and the incredible diversity of worlds it encompasses. So there we have it, almost everything you could possibly wish to know about the utterly fascinating world of Europa. Our cosmic journey now guides us further outward, towards Ganymede, the third of Jupiter's Galilean moons. Ganymede holds a special distinction. It is the largest moon known to us in the entire solar system, a colossal world that boasts the most extensive water ocean in our cosmic neighborhood. But beyond its sheer scale and the immensity of its subsurface water reserves, Ganymede harbors another profound mystery, a secret buried deep beneath its ancient surface, a phenomenon that truly sets it apart from anything else we have encountered before. Within the vast retinue of Jupiter's 79 diverse moons, Ganymede stands as the largest of the four Galilean giants. Its impressive diameter measures a staggering 5,268 kilometers. To provide a tangible sense of its colossal size, consider this: Ganymede is approximately 0.41 times the diameter of Earth, making it a truly planetary, scale body. Furthermore, it is even slightly larger, by about 1.02 times, than Titan, Saturn's colossal moon, which was previously thought to be the largest. Titan, however, initially appeared bigger due to its incredibly thick, hazy atmosphere, which extends for hundreds of kilometers into space, artificially inflating its perceived size. Ganymede's sheer volume is equally impressive, exceeding that of the planet Mercury by a significant 26%. Yet, despite its greater volume, Ganymede does not possess as much mass as Mercury. This discrepancy arises from a fundamental difference in composition. Ganymede's average density is a relatively low 1.9 grams per cubic centimeter, a stark contrast to Mercury's much higher density of 5.4 grams per cubic centimeter. This lower density is a direct consequence of Ganymede's unique makeup. Like its icy sibling Europa, Ganymede is enveloped by a thick, formidable crust of water ice, which plunges to depths of up to 150 kilometers. Beneath this expansive icy shell, scientists are confident that a vast, global ocean of liquid water sloshes, a truly immense body of water. And when we speak of vast, we truly mean it. This subterranean ocean is so colossal that it is estimated to contain more water than all the oceans and seas on Earth combined. Its average depth is thought to be around 100 kilometers, making it 10 times deeper than the deepest point in our own terrestrial oceans. This abundance of water signifies that Ganymede's composition is roughly 50% rock, with the remaining half consisting of water and smaller quantities of various other ices and metallic elements. This structural makeup seems rather fitting, given the moon's namesake. In classical Greek mythology, Ganymede was a beautiful young boy, whom Zeus, known to the Romans as Jupiter, admired and carried away to serve as the cup-bearer to the gods. It appears serendipitous, then, that the moon Ganymede, too, carries such an extraordinary abundance of water in its celestial embrace, eternally serving its planetary overlord. Intriguingly, Ganymede also possesses a tenuous atmosphere, an exceedingly thin veil of gas that contains oxygen. Now, upon hearing this, one might naturally ponder, with all this water and an oxygenated atmosphere, is it plausible that life could exist on Ganymede? While the possibility is certainly not dismissed outright, there are several characteristics of Ganymede that render the prospect somewhat less likely than on other potential candidates. Firstly, Ganymede's oxygen atmosphere is incredibly thin, an ethereal wisp of gas. Its estimated pressure ranges from a mere 0.2 to 1.2 micropascals, which translates to an astonishing 100 billion to 500 billion times less dense than Earth's atmospheric pressure at sea level. Such an atmosphere would be utterly impossible for human beings to breathe, offering no protection from the harsh vacuum of space. Secondly, while our own planet Earth has unequivocally demonstrated that thriving ecosystems can flourish in the profound depths of its oceans, entirely independent of sunlight for sustenance, fueled instead by geothermal energy, there could be a significant impediment preventing such life from arising on Ganymede. The sheer depth of Ganymede's ocean presents a unique challenge. The immense pressure exerted by the colossal weight of the overlying water and ice could, theoretically, compress the water at its very bottom back into a solid state, forming a layer of high-pressure ice. On Earth, life in the deepest parts of our oceans thrives thanks to the continuous expulsion of mineral-rich fluids from hydrothermal vents, which emerge directly from the planet's rocky, geothermally active core. However, with such an incredibly thick layer of high-pressure ice potentially separating Ganymede's liquid ocean from its rocky core, it seems improbable that these life-sustaining mineral-rich fluids could effectively reach the liquid water layer. For this reason, Europa, Ganymede's neighboring moon, is generally considered a more likely candidate for harboring life, precisely because its ocean is believed to be in direct contact with its rocky seafloor. However, a fascinating counter-argument suggests that if Ganymede's ocean is sufficiently salty, and there is a growing body of evidence supporting this idea, it could drastically alter the moon's internal structure. Models incorporating a salty ocean propose that Ganymede might possess multiple distinct layers, separated by various sheets of ice. In such a scenario, the innermost layer of liquid water could indeed be in direct contact with the rocky core, significantly increasing the chances for geothermal activity and, consequently, the potential for life to exist within that deepest watery realm. But beneath Ganymede's vast ice and water layers, there exists something else, something truly surprising and utterly unique, a profound enigma that scientists currently lack a definitive explanation for. Somehow, by some unknown mechanism, Ganymede is generating its own intrinsic magnetic field. The existence of Ganymede's magnetic field was first unveiled by an international team of scientists in 1996, when the Galileo spacecraft commenced a series of close flybys of the colossal icy moon. The most compelling indicator of a magnetic field is the presence of auroras, those breathtaking displays of light in a planet's or moon's atmosphere. Incredibly, auroras were indeed detected within Ganymede's tenuous atmosphere. Not only that, but as the Hubble Space Telescope meticulously observed Ganymede over an extended period, it became apparent that these auroral displays did not wobble or shift as much as theoretical models had predicted. This observed stability is believed to be a result of a phenomenon known as magnetic friction, occurring within a salty water ocean situated beneath the surface, further strengthening the case for a subsurface ocean. A magnetic field is of immense significance, particularly in the context of habitability, as it is the very feature on Earth that shelters our planet from the relentless, damaging onslaught of solar radiation, thereby enabling all forms of life to flourish and evolve. However, the magnetic field surrounding Ganymede, while present, is not sufficiently strong or extensive to completely protect it from such radiation. Nestled deep within Jupiter's incredibly powerful magnetic field and its formidable radiation belts, Ganymede is still subjected to a significant battering of high-energy particles. Even with its own magnetic shield, Ganymede's surface still receives an estimated 5 to 8 rem of radiation, a dose potent enough to cause severe illness or even death in a human exposed for just 2 months. Nevertheless, this level of protection is still considerably better than that experienced by its closer, orbiting Galilean neighbors, Io and Europa. The perplexing question that continues to challenge scientists is precisely why this magnetic field exists on Ganymede at all. On our planet, Earth's magnetic field is generated by the churning, convective movements of hot, molten iron within its core. These massive currents of electrically conductive liquid iron generate powerful electric currents, which in turn produce the magnetic field that envelopes us. However, this dynamic process should not, by all conventional scientific understanding, be occurring on Ganymede. Ganymede is considerably smaller than Earth, and given its size and inferred composition, scientists have long believed that its core should have cooled down sufficiently over billions of years to have solidified into a solid mass, rather than remaining in a molten, liquid state. A solid core would effectively prevent the movement of electrons through convection, thereby precluding the generation of a magnetic field. Furthermore, none of Jupiter's other moons possess an intrinsic magnetic field. In fact, Ganymede holds the singular distinction of being the only moon in our entire solar system known to generate its own magnetic field. So, what precisely is happening within this enigmatic giant? Scientists, while not yet possessing a definitive answer, hypothesize that the solution might lie in Ganymede's extraordinary and complex gravitational relationship with its colossal parent planet, Jupiter, and its neighboring Galilean moons, a process known as tidal heating. Ganymede completes an orbit around Jupiter approximately once every 7 Earth days, following a slightly eccentric path. This eccentricity means that at certain points in its orbit, Ganymede is closer to Jupiter than at others. When any celestial object comes under the influence of a strong gravitational force, it experiences a stretching effect, elongating in the direction of that force as its mass is pulled towards the source of gravity. Conversely, as the object moves further away from the source of gravity, it begins to compress back towards its original, more spherical shape. Because Ganymede's orbit around Jupiter is perpetually eccentric, it is constantly subjected to varying degrees of gravitational pull, causing it to continuously stretch and contract, a rhythmic kneading of its entire body. To visualize this phenomenon, consider a simple analogy. Have you ever repeatedly pulled and stretched a piece of blue tack or modeling clay in your hands, only to then push it back into a ball shape? If you have, you might have noticed that after a while, the material becomes surprisingly warm. This warmth is generated because the act of stretching and compressing produces internal friction as the material rubs against itself. On the immense scale of moons and planets, this friction accumulates into substantial amounts of heat, a process known as tidal heating. Adding to this complex interplay, Ganymede has formed a remarkably stable and precise orbital resonance with two of its fellow Galilean moons, Io and Europa. This intricate gravitational dance is known as a Laplace resonance. For every single orbit Ganymede completes around Jupiter, Europa will complete exactly twice, and Io will complete precisely 4 times. This mathematically precise configuration is not a happenstance. It is compelling evidence of the moon's profound gravitational influence upon one another, a meticulously balanced system striving to conserve its collective angular momentum. However, this perpetual gravitational interaction means that Ganymede is under constant gravitational stress, ceaselessly tugged and pulled by the combined gravities of its powerful neighbors and Jupiter itself. This continuous stress generates a significant amount of internal heat through tidal heating. Therefore, it is plausible that this tidal heating mechanism is sufficiently warming Ganymede's interior, maintaining its core in a liquid state despite its relatively small size. If its core remains molten, then the convective movements within it could indeed continue to generate the moon's unique magnetic field, providing a plausible explanation for this enduring enigma. Scientists do not yet know for sure, but this theory offers a compelling explanation. This same tidal heating mechanism could also potentially explain why Ganymede's surface presents such an interesting and diverse appearance. You may have noticed, upon observing images of Ganymede, that its surface is distinctly divided into 2 primary types of terrain: large, dark regions that encompass approximately 1/3 of its surface, and lighter, brighter regions that make up the remaining 2/3. By meticulously examining the density and distribution of impact craters on these 2 distinct sections, scientists have been able to deduce that the dark regions are, in fact, considerably older than the lighter ones, as they bear the scars of a greater number of ancient impacts. These heavily cratered, dark terrains are believed to be remnants of Ganymede's original crust, dating back to the very early days of the solar system. The lighter regions, while possessing fewer craters, are characterized by a striking landscape of long, parallel ridges and grooves. These impressive formations can reach heights of up to 700 meters and stretch for thousands of kilometers across the moon's surface, creating a truly awe-inspiring vista. Again, the precise formation mechanism of these enigmatic ridges remains a subject of ongoing scientific inquiry. One leading explanation posits that these features are the result of intense tidal forces stretching out the moon's surface during a period of significant geological instability in Ganymede's ancient history. Perhaps these very same powerful tidal forces, which stretched and fractured the crust, were also responsible for sufficiently warming Ganymede's core, thereby preserving its liquid state and allowing its magnetic field to persist over billions of years. Whatever its ultimate cause, Ganymede's magnetosphere has proven instrumental in assisting scientists in understanding the moon's internal composition. By precisely measuring and mapping the areas where auroras appeared in Ganymede's tenuous atmosphere, scientists were able to confirm, with remarkable certainty, the existence of Ganymede's vast subsurface ocean. This incredible feat of remote sensing allowed us to peer into the moon's hidden depths, all without ever having to physically set foot on its icy surface. As for the remaining mysteries of Ganymede, perhaps the European Space Agency's JUIC mission, the Jupiter Icy Moons Explorer, will provide us with some of the much-anticipated answers. The ESA spacecraft, which was successfully launched in 2023, is on its way to the Jovian system. While it won't achieve orbit around Ganymede for several years, its primary objective is to meticulously investigate the inner workings and surface features of a number of Jupiter's moons, including our colossal, magnetic giant, Ganymede. Until then, many of Ganymede's profound secrets may, for a little while longer, remain just that, a captivating mystery. Our cosmic expedition now carries us to Callisto, the outermost of Jupiter's 4 Galilean moons. Despite holding the distinction of being the third largest moon known in our solar system, I suspect that the majority of people would be hard-pressed to recall even a single definitive fact about it. Is it merely a dull, uninteresting world, or do we simply lack sufficient knowledge about it? The truth, as we shall uncover, is far more nuanced and, indeed, far from boring. In fact, we possess more information about Callisto than you might initially assume, and its ancient, scarred face holds a unique narrative within the Jovian system. Let us begin by establishing Callisto's place within the grand architecture of Jupiter's moons. Callisto ranks as the third largest moon in the entire solar system, a truly substantial celestial body only marginally smaller than the planet Mercury itself. Its diameter spans an impressive 820 kilometers across. However, while its diameter is only 58 kilometers less than that of Mercury, Callisto possesses only 1/3 of the mass of the planet. This significant difference in mass, despite similar sizes, indicates that Callisto is considerably less dense than Mercury, and consequently, its gravitational pull is substantially weaker. As the second largest of the Galilean moons, Callisto distinguishes itself by orbiting Jupiter at a much greater distance than its 3 inner siblings. This expansive orbital path means it takes Callisto a comparatively leisurely 17 Earth days to complete a single revolution around Jupiter, maintaining an average distance of approximately 1.9 million kilometers from the gas giant. Even at this considerable remove, Callisto, like its inner counterparts, is tidally locked with Jupiter, meaning that the same hemisphere of Callisto perpetually faces its colossal parent planet. Crucially, however, Callisto's distant orbit means that it is not locked in the intricate 4:1 orbital resonance that characterizes Europa, and Ganymede. Furthermore, scientific consensus suggests that Callisto has never been part of this resonance, preserving its orbital independence. Callisto possesses an exceedingly tenuous atmosphere, an ephemeral wisp of gas primarily composed of carbon dioxide, with the speculative possibility of oxygen also being present, though oxygen has not yet been definitively detected. We know, however, that this atmosphere is so incredibly thin that the individual molecules contained within it rarely, if ever, collide with one another, essentially behaving as free particles. Theoretically, such a fragile atmosphere should be rapidly stripped away by various atmospheric loss processes within a mere 4 years. Scientists hypothesize that Callisto's crust continuously replenishes these lost atmospheric particles through the slow process of sublimation, where solid carbon dioxide ices on the surface directly transition into gas. This ongoing replenishment is evidenced by some intriguing surface features. Now, we turn our gaze to Callisto's surface, one of the most ancient and remarkably preserved landscapes in the entire solar system, with compelling evidence placing its formation at over 4 billion years old, dating back to the very dawn of planetary accretion. What you will immediately notice is the distinctly speckled nature of Callisto's face. Its entire surface is utterly blanketed with impact craters of varying sizes, more so than any other celestial object we have ever observed. In fact, its surface is so heavily cratered that it is considered to be in a state of saturation, meaning that any new impact crater is highly likely to simply overlap and obliterate an existing one. In the profound absence of any significant geological activity, cratering has been, perhaps, the sole process that has vastly impacted and shaped Callisto's appearance throughout its immense lifetime. Why, then, is Callisto's surface so extraordinarily old and preserved, especially when compared to the surfaces of many other bodies in our dynamic solar system? The answer lies in the fundamental processes of geological activity. On geologically active planets, such as Earth, a myriad of powerful processes work relentlessly to erase almost all evidence of past impacts. Earth, for instance, possesses one of the least cratered surfaces in the solar system, precisely because so much dramatic activity continuously reshapes its exterior. We have dynamic weather systems, flowing water, the pervasive influence of plant life, powerful volcanism, the slow but relentless march of tectonic plates, and, more recently, the transformative impact of human activity. All these forces conspire to break apart, wear down, uplift, and ultimately obscure the ancient scars of impact events. Even other Jovian moons, like the volcanically active Io or the geologically dynamic Europa, exhibit comparatively fewer craters thanks to the immense tidal forces exerted by Jupiter, which drives significant geological activity on their surfaces, constantly resurfacing them. This, however, is not the case for Callisto. Callisto shows virtually no signs of internal geological processes, such as volcanism or the movement of plate tectonics. Consequently, its ancient surface has remained remarkably intact, a frozen tableau preserved over billions of years. The limited influence of tidal forces and the consequent absence of internal geological activity impacts Callisto in yet another, very unique way. There are literally no mountains of any significant height to speak of across its entire surface. When Callisto initially formed, in the tumultuous, nascent stages of the solar system, it was likely an ocean world that has since gradually frozen over. And apart from the relentless bombardment of meteors, which pockmarked its surface, it has remained largely unchanged ever since, a fossilized relic of the early solar system. So, let's take a closer look at some of these colossal craters, for some of the biggest are truly impressive and unique structures. Consider Asgard, for instance, the second largest impact crater on Callisto, an immense basin measuring an astonishing 600 kilometers in diameter. And then there is Valhalla, the undisputed largest multi-ring impact crater in the entire solar system, boasting a truly colossal diameter of 800 kilometers. These immense craters, with their characteristic multiple rings, contribute significantly to Callisto's unique appearance, setting it apart from other heavily cratered worlds. With these colossal craters, the impactor responsible for their creation was so enormous and energetic that it may have completely punctured Callisto's relatively thin icy crust, causing the subsurface material to well up and eventually refreeze. The lighter, smoother patches often observed in the very centers of these multi-ring structures are believed to be these refrozen areas. Zooming in on these central regions, you'll notice a distinctly mottled, almost speckled appearance. There often seems to be a significant difference in contrast between brighter, elevated knobs and the darker, lower plains surrounding them. These central regions are also considerably less cratered than the rest of Callisto's ancient surface, which would logically make sense if the plains truly represent a refrozen surface, likely making them a staggering 2 billion years younger than the most ancient, heavily cratered terrains of Callisto. The concentric rings, radiating outwards from these central impact points, are believed to be colossal fractures in the crust, a pattern of concentric failure in the Moon's brittle, icy shell caused by the immense shockwave of the impact. Intriguingly, even within these vast rings, the brighter, elevated knobs are still visible. So, what exactly are these mysterious knobs? Scientists believe they are the degraded, eroded remnants of the countless crater rims that adorned Callisto's surface in its distant past. The precise reasons for their extensive degradation over immense timescales are not fully understood, but perhaps it is due to the cumulative effects of countless micrometeorite impacts, or simply the slow, inexorable process of ice sublimating over geological epochs. They appear brighter than the lower plains because the darker, rocky debris from the meteors and micrometeorites would have gradually fallen down the slopes of these knobs over billions of years, leaving the purer, brighter ice exposed at their summits. Smaller impact craters on Callisto are also fascinating due to their own unique characteristics. Most impact craters on Callisto are notably shallower compared to those found on, say, our own moon. Take the Lore impact structure, for example. It measures well over 100 kilometers wide, yet it is only a mere 600 meters deep. This comparative shallowness could be attributed to several factors. Perhaps the impactor itself was breaking apart before it struck the surface, causing a more spread-out, shotgun effect impact. Alternatively, it's possible that the surface has since gradually leveled off due to the seismic reverberations and material redistribution from other, larger nearby impacts that occurred later in Callisto's history. This particular crater is believed to be at least 1 billion years old. Yet you can still clearly discern the ejecta. The material blasted outwards from the impact, streamed away from the central point. Clear evidence of how remarkably unchanging this ancient moon truly is. In some craters, such as the Har crater, an interesting feature is observed: a large, central dome. With typical large impacts on other celestial bodies, you often see a few concentric rings and a raised peak in the center, a phenomenon clearly evident on our own moon. However, Callisto presents some truly remarkable examples of large craters where the exact opposite occurs. Look at Tinger, for instance. Instead of a central peak, there is actually a distinct pit in the very center of the crater. Why does Callisto exhibit such unique crater morphologies? This unusual characteristic could be attributed to the fact that Callisto's crust is not only brittle, but also relatively thin, potentially overlying either soft, deformable ice or, as we shall discuss, a salty subsurface ocean. Estimates place the thickness of this icy crust at a range of 80 to 150 kilometers. The Galileo space probe, which spent several years meticulously studying the Jovian system, dedicated a significant portion of its mission to examining the Galilean moons, including Callisto. Galileo's observations revealed that Jupiter's powerful magnetic field could not fully penetrate through Callisto, implying the existence of a highly electrically conductive layer situated beneath its surface, at a depth of at least 10 kilometers. Such a conductive layer could not be readily explained by pure ice or silicates, unless the ice layer is at least partially molten, or unless very large temperature gradients can be maintained below the ice to create a conductive effect. Further data also suggests that Callisto likely possesses a small, undifferentiated silicate core at its very center, with a radius of approximately 600 kilometers. This naturally leads us to a pivotal question: can Callisto, like other icy worlds thought to harbor subsurface water oceans, be conducive to life? Life as we currently understand it fundamentally requires liquid water and a source of energy to exist. While Callisto might indeed possess an ocean of liquid water beneath its surface, its immense distance from the Sun, approximately 800 million kilometers, means it receives barely any heat from our star. Furthermore, the notable absence of significant tidal forces, unlike its inner Galilean siblings, does not contribute to internal heating. This leaves radioactive elements within its core as the only conceivable source of heat capable of warming a hypothetical subsurface ocean, should it exist. Unfortunately, even a direct visit to Callisto might not immediately resolve these questions. Moons like Europa and Enceladus, for example, exhibit active vents that eject plumes of water directly from their subsurface oceans into space. These plumes offer a remarkable opportunity to investigate the habitability prospects of these worlds without the daunting task of actually penetrating their thick icy crusts and descending into the oceans themselves. No such active vents have been observed on Callisto. Therefore, scientists would face the enormous challenge of having to physically penetrate its thick crust in order to directly sample and analyze its interior, a monumental engineering feat. All these factors combined lead scientists to conclude that, unfortunately, the environmental conditions necessary for the formation and sustenance of life appeared to be considerably less favorable on Callisto than on other promising icy worlds in our solar system. Nevertheless, Callisto should by no means be ignored. In fact, if humanity ever endeavors to extensively explore the outer solar system, Callisto could prove to be an absolutely perfect base of operations. You see, orbiting at a considerable distance of 1.9 million kilometers from Jupiter, Callisto is strategically located beyond the most intense regions of Jupiter's main radiation belt. This means that its environment is thousands of times more conducive and hospitable to human exploration than that of its inner, more irradiated moons. Furthermore, Callisto possesses abundant reserves of water ice, which could be readily utilized for a variety of purposes vital for deep space missions. This includes the production of propellant for spacecraft and, of course, as the essential staple to sustain human life. The process of separating hydrogen from oxygen in water ice would not only provide breathable oxygen for astronauts, but also hydrogen, a key component for rocket fuel. Callisto's geological stability, a direct result of its lack of internal activity, would make the construction of permanent structures on its surface a relatively worry-free endeavor. And the absence of colossal mountains or deep trenches means that travel across its surface would be significantly faster, easier, and more energy efficient. From a strategically located base on Callisto, we could more safely and effectively explore the inner Jovian system, observing its dynamic moons and rings from a secure distance, or utilize it as a vital way station for launching missions further into the vast, unexplored reaches of the outer solar system. Lifting off from Callisto's surface would be ideal thanks to its very low gravity, requiring far less fuel than launching from a more massive body. Moreover, spacecraft could then utilize a close flyby of Jupiter to gain a powerful gravity assist, slingshotting them deeper into space. It is true that this remains a futuristic prospect, but if humanity is destined to become a truly space-faring species, establishing such a base on Callisto represents a distinct and highly plausible possibility. While the Galileo mission performed an admirable job of studying Callisto during its limited flybys, there still exist significant gaps in our understanding, a multitude of questions that eagerly await answers. With any luck, we will begin to fill these informational voids with data from the European Space Agency's Jupiter Icy Moons Explorer (JUIC) mission, which, as mentioned, launched in 2023 and is set to arrive in the Jovian system by 2030. JUIC will embark on a comprehensive exploration of Jupiter and three of its largest moons, Ganymede, Callisto, and Europa. ESA has meticulously planned several close flybys of Callisto during this mission, which may provide invaluable new insights into fundamental questions such as, does Callisto truly possess a subsurface ocean? And if so, are the conditions within that ocean, or can they ever be, conducive to sustaining life? Beyond these immediate inquiries, there are also the myriad questions we haven't even thought to ask yet. The unexpected discoveries that invariably emerge from new observations. Who knows what further secrets we will still uncover about this incredible, ancient moon? So there we have it. Almost everything you could possibly wish to know about the Galilean moons of Jupiter, a quartet of worlds each unique, each holding profound mysteries and potential. Our journey now takes us far beyond the Jovian system, into the colder, more distant reaches of our solar system. In the vast expanse surrounding the majestic, ringed giant Saturn lies a world sculpted from ice and shrouded in mystery. This is Rhea. Rhea is Saturn's second largest moon, though its colossal sibling, Titan, often overshadows it, capturing most of the scientific and public attention. Yet, Rhea is a fascinating place in its own right, a celestial body that harbors a multitude of secrets and wonders, waiting patiently to be unveiled. Imagine towering ice cliffs, hundreds of meters high, carving dramatic landscapes into its surface. Ponder an internal structure that, for decades, defied conventional scientific models. And then, consider the enigmatic discovery of something around this moon that is equally as strange as the profound absence of something else that scientists initially expected to find. It is time for this often overlooked moon to step out from the long shadow cast by its larger sibling. Let us embark on a journey of discovery to learn all there is to know about Rhea. Rhea's discovery dates back to December 23, 1672, credited to the brilliant Italian astronomer Giovanni Domenico Cassini. Cassini, a pivotal figure in the history of astronomy, made numerous profound contributions to our understanding of Saturn and its complex family of moons. Rhea, named after the formidable Titan goddess in Greek mythology, has captivated astronomers and planetary scientists for centuries, its distant light a constant invitation to curiosity. Let's begin with the fundamental characteristics of this icy world. Rhea is, as mentioned, the second largest moon of Saturn, surpassed only by the colossal, shrouded Titan. With a diameter of 528 kilometers, it is roughly half the size of Earth's own moon. To offer a more relatable scale, if we were to hypothetically place Rhea next to Earth, its diameter would stretch approximately from London to Warsaw, a truly significant distance. Rhea traces its orbit around Saturn at an average distance of about 527,000 kilometers, completing one full revolution every 4.5 Earth days. Like many of the larger moons in our solar system, Rhea is locked in a state of synchronous rotation with Saturn, meaning that it always presents the same face to its colossal parent planet. The surface of Rhea is one of the most remarkably reflective in our entire solar system, possessing an albedo of 0.7. This means that Rhea reflects an astonishing 70% of the sunlight that strikes its surface, causing it to appear as a brilliant, almost blindingly white orb against the deep, velvet blackness of space. This exceptionally high reflectivity is directly attributable to its primary composition. Rhea's surface is predominantly made of water ice. However, this does not imply a featureless, pristine sheet of ice, far from it. The moon's surface is heavily cratered, a stark testament to a long, tumultuous history of ancient impacts and cosmic collisions. Each crater, a silent scar, tells a story of the violent forces that shaped this distant world over billions of years. The largest of these impact craters, appropriately named Mamaldi, spans an impressive 480 kilometers in diameter, a distance roughly equivalent to that from Paris to Amsterdam. These craters are not merely superficial blemishes on Rhea's surface. They are, in essence, geological windows into the moon's deep past and its internal composition. Observations have revealed that the bottoms of some of these ancient craters appear noticeably darker than the surrounding terrain. This difference in coloration could indicate that the immense force of the impacts excavated material from beneath Rhea's bright, pristine surface, potentially exposing darker, amorphous water ice or even impact melt, material that was briefly liquefied by the energy of the collision before refreezing. In one particular photograph, we can clearly observe a prominent crater situated in Rhea's southern hemisphere, surrounded by a bright halo of ejecta, the material blasted out from the impact. However, one of the most intriguing and visually captivating features of Rhea is its intricate system of bright, wispy streaks that elegantly crisscross its surface. These enigmatic markings were first observed in detail by the Voyager space probes during their flybys in the early 1980s. At that time, their true nature remained largely a mystery. It wasn't until the Cassini mission, decades later, provided us with incredibly high, resolution images that the true character of these wisps was finally understood. Initially, Scientists speculated that these streaks might be deposits of frost or freshly fallen ice. However, the Cassini images dramatically revealed them to be colossal ice cliffs, some of which tower hundreds of meters high. These majestic cliffs are believed to be the result of past tectonic activity within Rhea, where the moon's icy crust fractured and some sections were dramatically thrust upwards, creating these spectacular scarps. These features offer invaluable clues about Rhea's geological history and the complex processes that have sculpted its ancient surface over billions of years. But Rhea's mysteries are not confined to its surface. In 2010, data transmitted back from the Cassini spacecraft led to a truly surprising and unexpected announcement. Rhea appeared to possess a tenuous atmosphere, or more accurately, an exosphere. While a minuscule amount of gas around Rhea was generally anticipated by scientists, the discovery that there was enough to be precisely measurable was genuinely unforeseen. The detected exosphere was found to consist primarily of oxygen and carbon dioxide, with the oxygen being an astonishing 5 trillion times less dense than Earth's atmosphere at sea level. While incredibly thin and utterly unbreathable, the mere presence of this atmosphere sparked a flurry of intriguing questions regarding its origin and its long-term sustainability. One prevailing theory suggests that the oxygen is continually produced by the decomposition of water ice on Rhea's surface. This process occurs when Rhea's ice is struck by energetic ions originating from Saturn's powerful magnetosphere, causing the H2O molecules to split apart. The carbon dioxide, on the other hand, is thought to be the result of organic molecules, likely present in trace amounts on the surface, being oxidized by the newly generated oxygen within the exosphere. This remarkable discovery made Rhea the first moon, other than Jupiter's larger moons, Ganymede and Europa, to be definitively known to possess an oxygen atmosphere. It also opened up entirely new avenues for research into the complex and dynamic interactions between Saturn's diverse array of moons and the planet's powerful, extensive magnetosphere. Rhea's exterior, with its ancient craters and towering ice cliffs, is undeniably fascinating, but what about its interior? Let us now delve deeper, quite literally, beneath its icy shell. While we are currently unable to directly observe what lies beneath Rhea's opaque, icy surface, scientists have employed various ingenious methods to infer its internal structure, primarily based on its average density. Rhea's average density is a relatively low 1.236 grams per cubic centimeter, which is only slightly higher than that of pure water at 1 gram per cubic centimeter. From this, we can deduce that Rhea is predominantly composed of water ice, making up approximately 75% of its total mass, with a smaller fraction of rocky material accounting for the remaining 25%. Due to this composition, Rhea has often been described, somewhat colloquially, as a frozen dirty snowball, a stark contrast to moons like our own, which are primarily solid, rocky bodies. When the Cassini spacecraft conducted its close flybys of Rhea, its sophisticated instruments also provided invaluable data concerning Rhea's composition. Spectroscopic observations, which analyze the light reflected from the surface to identify chemical constituents, confirmed that water ice is indeed the overwhelmingly dominant component of Rhea's surface. However, these observations also detected the presence of other materials. One particularly surprising discovery was the identification of carbon dioxide trapped within the surface ice. This finding suggests that Rhea's ice is not merely pure water, but contains other compounds, possibly including complex organic molecules, hinting at a more intricate chemical history. Based on its higher moment of inertia, a measure of how resistant an object is to changes in its rotation, most scientists have long believed that Rhea is not differentiated into distinct internal layers. Instead, it was thought to be a relatively homogeneous mixture throughout, with the possible exception of a very small central core. This model suggested a uniform blend of ice and rock from surface to center. However, some scientists challenged this established model. In 2006, a paper published in the journal Icarus put forth the intriguing hypothesis that Rhea might, in fact, harbor a layer of liquid water beneath its surface, a subsurface ocean. While this idea remains highly speculative and is not as strongly supported by evidence as the subsurface oceans on moons like Europa or Enceladus, it represents a captivating possibility that future missions might one day investigate. The confirmed presence of such an ocean would carry significant implications for Rhea's potential habitability, or at least for the conditions necessary for liquid water to persist in the frigid depths of the outer solar system. Rhea's interior holds its own share of mysteries, but one of the more puzzling features of Rhea, particularly for an object of its size, is its distinct shape. While many large moons and planets, due to the overwhelming force of their own gravity, tend towards a near-perfect sphere, Rhea is noticeably non-spherical. It is slightly flattened at its poles and bulges outwards at its equator, a shape technically described as a triaxial ellipsoid. What makes this particularly strange is that Rhea's observed shape does not precisely match what scientists would expect based solely on its rotation rate. This intriguing discrepancy has led researchers to propose that Rhea might possess a non-uniform internal structure, perhaps with denser material concentrated in certain areas away from its exact center, influencing its overall form. Now, let's recount one of the most exciting and fruitful periods in Rhea's recent observational history: the close flybys conducted by the Cassini mission. The Cassini spacecraft, a remarkable collaborative project involving NASA, ESA, and the Italian Space Agency, spent over a decade meticulously studying the intricate Saturnian system, including numerous close encounters with Rhea. The closest of these dramatic flybys occurred on January 11, 2011, when Cassini passed a mere 76 kilometers above Rhea's surface, a truly breathtaking proximity. The final close flyby took place on March 9, 2013, with Cassini passing approximately 997 kilometers above Rhea. These incredibly close approaches allowed the spacecraft to capture images of unprecedented detail, revealing Rhea's heavily cratered terrain in exquisite clarity. Crucially, Cassini also gathered invaluable data about the Moon's composition and, significantly, was able to definitively determine that Rhea does not possess an internal magnetic field, unlike Ganymede. These flybys provided us with our finest, most intimate views yet of Rhea's surface features. They revealed a landscape predominantly characterized by two distinct types of terrain, a pattern first observed in the earlier Voyager missions. The heavily cratered areas, which we've discussed, are widely believed to be extremely ancient, possibly dating back to the very earliest epochs of the solar system's formation. These primordial surfaces serve as an invaluable geological record, preserving the evidence of the intense bombardment that characterized the solar system's tumultuous youth, a time when countless asteroids and comets ceaselessly impacted nascent worlds. The smoother, younger plains, on the other hand, are thought to be the consequence of significant resurfacing events. This resurfacing could have been caused by material ejected from exceptionally large impact events, which would have subsequently fallen back to the surface, effectively filling in older craters and creating broad, more uniform regions. However, perhaps one of the most intriguing results stemming from the Cassini mission was not what it discovered, but rather what it failed to find. Prior to Cassini's arrival in the Saturnian system, some scientists had put forth the hypothesis that Rhea might potentially possess its own system of rings, similar to those famously encircling Saturn itself. This intriguing idea was predicated on unusual measurements of electron densities detected around Rhea by Cassini in 2005. These anomalies hinted at the presence of a localized, charged particle environment that could be explained by a ring system. Yet, despite meticulous and comprehensive searches conducted during its close flybys, Cassini ultimately found no definitive evidence of rings around Rhea. This non-detection doesn't entirely preclude the possibility of some incredibly faint, diffused debris disk around Rhea, but it certainly renders such a scenario far less probable than initially thought. Another fascinating aspect of Rhea is its unique position within Saturn's incredibly complex and dynamic system of moons and rings. Rhea's orbit around Saturn actually places it within what is known as the E ring, a remarkably diffuse and expansive ring composed primarily of microscopic ice particles. This E ring is widely believed to be continuously replenished by the cryovolcanic eruptions, the icy geysers emanating from another of Saturn's intriguing moons, Enceladus, which we will explore in detail shortly. While Rhea itself does not appear to be geologically active in the same dramatic fashion as Enceladus, its location within this E-ring means it is in constant, albeit subtle, interaction with these tiny ice particles. Although Rhea resides in the outermost extremities of the E-ring, beyond where it is densest, this long-term interaction could subtly affect Rhea's surface properties, potentially contributing to the Moon's exceptionally bright, reflective appearance over immense timescales. As we reflect upon the wealth of knowledge we've accumulated about Rhea, it becomes abundantly clear that this moon, so often overshadowed by its more famous and dramatically active siblings, is a profoundly fascinating world in its own right. From its ancient, heavily cratered hemisphere, a silent witness to the solar system's dawn, to its relatively smoother, younger planes, from its incredibly tenuous exosphere, hinting at complex surface chemistry, to its unique place within Saturn's elaborate system of moons and rings, Rhea continues to captivate scientists and ignite our collective imagination. However, our exploration and understanding of Rhea are far from complete. Many fundamental questions remain tantalizingly unanswered. What is the precise nature of its enigmatic internal structure? How has it evolved over the immense span of billions of years since its formation? Could it, by some remote chance, harbor simple forms of life within a hypothetical subsurface ocean, if such an ocean were to exist and prove habitable? These profound questions, and many more yet to be formulated, patiently await future missions to the intricate and beautiful Saturnian system. While there are currently no dedicated missions specifically targeting Rhea in the immediate future, any subsequent spacecraft dispatched to study Saturn and its diverse family of moons will undoubtedly make observations of this intriguing world. As we bring our quiet journey to Rhea to a close, let us take a moment to truly appreciate the astonishing diversity of worlds that populate our solar system, from the scorching, cloud-veiled surface of Venus to the frigid, distant icy plains of Pluto, from the towering, ancient volcanoes of Mars to the potential subsurface oceans teeming with possibility beneath the icy shells of moons like Enceladus. Our cosmic neighborhood is an infinitely rich tapestry, brimming with wonders just waiting to be explored. Rhea, with its brilliantly reflective icy surface, catching the distant sunlight, stands as a quiet yet powerful testament to the boundless beauty and enduring mystery that pervades our universe. As we continue our ceaseless quest to explore and to learn, who knows what further, astonishing secrets this distant, enigmatic moon may yet reveal to us. Well, everyone, here it is, your most highly requested video, a deep dive into the colossal, enigmatic moon known as Titan. And to be fair, I can completely understand the intense curiosity surrounding it. Titan holds a multitude of unique distinctions that set it apart from every other moon in our solar system. It is the only moon known to possess a substantial, dense atmosphere, a thick, hazy shroud that completely obscures its surface from direct view. Furthermore, there is unequivocal evidence of stable bodies of surface liquid, lakes and seas. On Titan, a phenomenon otherwise found only on Earth. And perhaps most remarkably, humanity has actually visited this distant world, sending a probe to descend through its atmosphere and land upon its frigid surface, providing us with a wealth of real photographs and even video footage. Titan occupies the position of the sixth spherical moon orbiting Saturn. Unlike Jupiter's quartet of Galilean moons, which are all substantial in size, Titan stands alone in its colossal scale within the Saturnian system. The remainder of Saturn's moons are, by comparison, relatively small, often mere icy rubble. To offer a tangible sense of its sheer magnitude, Titan's diameter is a staggering 50% larger than that of Earth's moon, and it possesses an astonishing 80% more mass. In fact, it ranks as the second largest moon in the entire solar system, surpassed only by Jupiter's colossal Ganymede. It is worth noting that Titan does visually appear slightly larger than Ganymede if you were to place them side by side. However, this optical illusion is caused by Titan's incredibly thick atmosphere, which extends its apparent diameter significantly. Even setting aside this atmospheric ILO, Titan's true solid diameter is still larger than that of the smallest planet in our solar system, Mercury. Yet, despite its greater size, Titan is only about 40% as massive as Mercury, a clear indication of its relatively low density for its immense volume. Due to this low density, Titan's gravitational pull is quite weak, measuring only about 0.14 Gs or 1.35 meters per second squared. This is even less than the gravity experienced on our own moon. The moon's low density also strongly suggests that its composition is approximately half water ice and half rocky material. Unlike many other celestial objects of comparable size, Titan is believed to possess a differentiated interior, meaning it is structured into distinct layers. And, akin to a number of other large moons in our solar system, one of these layers is thought to be a vast, subsurface ocean of liquid, comprised of water and ammonia, situated beneath the moon's thick, icy crust. This liquid ocean is somewhat comparable to Earth's magma layer, which lies between our planet's core and crust. Its liquid state is maintained by a combination of internal heat, immense pressure, and to a certain degree, the incessant tidal forces exerted by Saturn. The existence of this hidden liquid layer was made considerably more probable by a remarkable discovery made by the Cassini spacecraft, which orbited Saturn for over a decade. Cassini detected extremely low-frequency radio waves in Titan's atmosphere. Titan's solid surface is not known to be a good reflector of such low-frequency radio waves, but a deep, electrically conductive liquid interior, like a salty ocean, would be. Another compelling piece of evidence is the observation that various surface features on Titan have shifted by up to 30 kilometers since Cassini began its observations. This significant displacement strongly implies that Titan's surface crust is not rigidly attached to its core, but rather floats freely upon this vast, subsurface ocean layer, allowing for independent movement. While there is currently no direct evidence of life on Titan, scientists do speculate that the conditions within this subsurface ocean could potentially be conducive to the emergence of life, albeit a type of life likely very different from what we understand on Earth. Unfortunately, if there were indeed life to be found, either on the surface or deep below, we will have to wait for a considerable period, as there are no currently planned missions specifically designed to investigate this intriguing possibility. For the foreseeable future, Jupiter's moon Europa is considered a more immediate and likely candidate for dedicated life detection missions. Titan's differentiated interior does not, however, produce an intrinsic magnetic field of its own. Nevertheless, Titan is still quite well protected from the destructive solar wind, as approximately 95% of its orbital path around Saturn lies safely within Saturn's own vast and powerful magnetosphere, a protective bubble of magnetic force. Titan completes one full orbit around Saturn approximately every 15 days and 22 hours. Its orbit possesses a rather large eccentricity, meaning it is not a perfectly circular path, but a noticeably elongated ellipse. Furthermore, its orbital plane is also inclined at a significant angle relative to Saturn's equatorial plane. However, these orbital characteristics do not necessarily imply that Titan is a captured object, like Neptune's moon Triton. Instead, much like Jupiter's Galilean moons, it is theorized that Saturn too once possessed several large moons in its distant past. Most of these, however, are thought to have been destroyed through colossal collisions and gravitational interactions, leaving Titan as the lone, victorious survivor of this tumultuous early period. Saturn's medium-sized moons, such as Iapetus and Rhea, are believed to be the scattered remnants of this chaotic beginning. Titan's day, much like the day on our own moon, is identical in length to its orbital period. This means that Titan's rotation is tidally locked to Saturn, perpetually presenting only one face to the planet. However, visually speaking, this tidally locked state makes little practical difference, as Titan's famously thick, hazy atmosphere completely obscures any view of its surface from an outside perspective. Conversely, if you were standing on Titan's surface, you might just be able to discern the faint, obscured outline of Saturn in the sky, though the view would be significantly veiled by the atmospheric haze. This also implies that if you were to stand stationary at a particular spot on Titan, Saturn would never appear to move across the sky, remaining fixed in its position. If we could somehow magically peel away Titan's omnipresent haze, this is what its surface might look like: a world of fascinating features hidden beneath the atmospheric shroud. This leads us directly to one of the most compelling and defining characteristics that truly sets Titan apart from all other moons in the entire solar system: its substantial and incredibly dense atmosphere. I vividly recall the first time I ever encountered a photograph of Titan. I was truly captivated, utterly blown away, as it had never occurred to my younger self that a moon could even possess an atmosphere, let alone one so thick and pervasive. I initially imagined it must have been a newly discovered planet. To me, what appears most striking and unusual about Titan's atmosphere is how far it stretches into space. When you view an image of Earth, its atmosphere appears to cling quite tightly to the planet, a relatively thin blue band. Titan, on the other hand, looks as though it is enveloped by a colossal, thick blanket extending far, far into the void. There are several compelling reasons for this dramatic difference. Firstly, while Titan is considerably smaller than Earth, its atmosphere is an astonishing 1.9 times more massive than Earth's, or expressed on a per-surface area basis, it is a staggering 7.3 times more massive. Secondly, Titan's gravitational pull is significantly weaker than Earth's, meaning it doesn't exert as strong a downward force on its atmospheric gases, allowing them to expand further outwards into space. The sheer mass of this atmosphere results in a surface pressure of 1.45 atmospheres, which is a remarkable 45% greater than the atmospheric surface pressure we experience on Earth. Comparing the two, one can truly appreciate the incredible extent to which Titan's atmosphere stretches into space. Its mesosphere alone extends to a height of 600 kilometers, whereas Earth's mesosphere terminates at a mere 120 kilometers. Even at a considerable distance of 975 kilometers, the Cassini spacecraft had to make precise adjustments to maintain a stable orbit, battling against the subtle yet persistent atmospheric drag. Like the planet Venus, Titan is a super-rotator, meaning its atmosphere rotates considerably faster than the Moon's solid body itself. This phenomenon is particularly pronounced at the poles, where each pole harbors a distinct polar vortex that completes a rotation once every 9 hours, in stark contrast to the Moon's solid rotation period of 16 days. These polar vortices appear to be permanent, colossal hurricanes, perpetually swirling at the moon's northern and southern extremes. So, what precisely does this dense, enigmatic atmosphere consist of, and why does it present such a distinctive orange hue? The atmosphere is overwhelmingly composed of nitrogen, accounting for approximately 98.4% of its composition. The remainder is primarily methane, with small, trace amounts of hydrogen. Additionally, there are minute quantities of various hydrocarbons, formed from the breakup of methane in the upper atmosphere by the relentless bombardment of UV light from the sun. It is these complex hydrocarbons, suspended as aerosols and fine particulates, that are believed to impart Titan its characteristic, hazy orange coloration. This constant photochemical breakup of methane into heavier hydrocarbons in the upper atmosphere presents a significant puzzle. If this process were not balanced by a continuous replenishment, Titan should have completely run out of methane within a relatively short geological timescale of approximately 50 million years, a mere blink compared to the immense age of the solar system. This implies there must be an ongoing source that replenishes the methane supply. The most likely candidate for this replenishment is cryovolcanism, where methane-rich liquid or slush erupts from below the surface. Intriguingly, however, the possibility of biological life as a source has not been definitively ruled out, though it remains a highly speculative hypothesis. The methane in Titan's atmosphere creates a pronounced greenhouse effect, which, in the absence of other factors, would significantly warm the moon. Conversely, however, the pervasive haze also reflects a considerable amount of incoming sunlight back into space, creating an anti-greenhouse effect that partially cancels out some of the potential warming from the methane. While Titan's upper atmosphere receives approximately 1% of the sunlight that Earth does, due to its immense distance from the Sun, a further consequence of this atmospheric reflection means that Titan's surface ultimately receives only about 0.1% of the sunlight that reaches Earth. The Huygens probe team, which designed the lander that touched down on Titan, likened the challenge of capturing photographs at this incredibly low light level to attempting to take pictures of an asphalt parking lot at dusk. A truly dim and challenging environment. All these factors combined mean that while the surface of Titan would be incredibly dark, a human standing there would primarily need two things to be comfortable: an oxygen mask to breathe as the atmosphere is nitrogen methanide, and exceptionally warm clothing to combat the extreme cold. It is indeed profoundly cold on Titan, with an average temperature of a frigid 180 degrees Celsius. This extreme cold ensures that any water on Titan remains permanently solid, existing as rock, hard ice that never melts, evaporates, or sublimes under normal conditions. Why, then, are there sometimes clouds on Titan? These are not water-ice clouds, but rather methane clouds, which means, astonishingly, it can and does rain liquid methane on Titan. In fact, the temperature on Titan is precisely within the range for methane to exist in its liquid state, 182.5 degrees Celsius, and boils at 161.5 degrees Celsius. This unique combination of temperature and surface pressure ignited immense excitement among scientists at the prospect of stable bodies of liquid hydrocarbons, lakes or seas, existing on Titan's surface, analogous to the water lakes and seas found on Earth. If such lakes truly existed on this distant moon, it would represent the first time this phenomenon had ever been directly observed outside of Earth. This very possibility was one of the primary driving forces behind the Cassini-Huygens mission to peer beneath that thick, hazy atmosphere and discover what lay hidden. The Huygens probe, named after Christian Huygens, the astronomer who discovered Titan in 1655, was meticulously designed to enter Titan's atmosphere and, ultimately, land on its surface. The distinct possibility of even landing on a liquid ocean was carefully factored into its design process. As the probe made its descent, its parachute deployed, slowly guiding it through the dense atmosphere. After an almost 3-hour journey, Huggins finally came to rest upon the solid surface of Titan. Sadly, it did not land in an active lake, but what it did observe provided compelling confirmation that methane lakes once existed in that very location. Huggins settled on what appeared to be a dried-up lake bed. The stones, visible in the surface photographs, are distinctly rounded, much like pebbles found in a riverbed or along the shore of a lake on Earth, indicating past fluvial erosion. From its orbital vantage point, the Cassini spacecraft was able to confirm that active methane lakes and seas are indeed still found on Titan today. Near the Moon's south pole, Cassini observed a large area that was later confirmed to be a lake named Ontario Lacus. This lake, while substantial, is about 20% smaller than its North American namesake, Lake Ontario, meaning it is still quite large, covering an area of approximately 15,000 square kilometers. On one side of Ontario Lacus, images reveal a remarkably smooth shoreline clearly eroded by waves, much like coastlines on Earth. On its western side, Cassini identified the first clear evidence of a river and a delta on Titan, indicating that liquid hydrocarbons flow down from higher plains to the lake, depositing sediments in a process strikingly similar to the formation of deltas on Earth. Ontario Lacus itself is remarkably shallow, estimated to be only between 40 centimeters and 3 meters deep, with the deepest point likely just over 7 meters. As Cassini's radar meticulously mapped this lake, it found that the lake did not exhibit waves larger than about 3 millimeters. This suggests that, at the time of observation, the surface would have appeared incredibly still, like a sheet of glass or a mirror. This doesn't necessarily mean that larger waves cannot form, unless the liquid itself is particularly viscous. More likely, it simply means that it was not a windy day when the observations were taken. Given Titan's atmospheric density and relatively low gravity, theoretical models suggest that waves on Titan should actually be considerably larger than those on Earth for a given wind speed. As the Moon's North Pole began to emerge from its prolonged 15-year winter, another significant lake was discovered, Jingpo Lacus. As Cassini passed by the Moon, sunlight directly reflected off the surface of Jingpo Lacus, like a mirror, straight into Cassini's view, allowing for its detection. Upon further, more detailed observation, Cassini was able to detect additional, compelling evidence of moving liquid on Titan, as clearly demonstrated by the intricate networks of rivers flowing into this lake. The second largest lake discovered on Titan is Ligeia Mare, located in the Moon's North Polar region. This colossal body of liquid is larger than Lake Superior on Earth, encompassing a surface area of an astonishing 126,000 square kilometers. While certain parts of Ligeia Mare are reasonably shallow, its average depth is considerably greater than that of Ontario Lacus, estimated at 50 meters, with some sections potentially reaching depths of over 200 meters. Numerous rivers can be seen flowing into this vast lake, and large islands dot the surrounding area. Here, Cassini made a particularly curious observation, dubbed the Magic Island. The inexplicable appearance and disappearance of what seemed to be an island within Ligeia Mare. While scientists are still unsure of the exact phenomenon, leading theories propose that it could have been silt suspended in the lake, rising bubbles of methane or nitrogen, or even subsurface ice rising to the surface as the lake warmed during Titan's spring. Whatever its cause, it remains a very curious and intriguing mystery. The largest known lake on Titan, and indeed the largest body of liquid in the entire solar system outside of Earth, is the colossal Kraken Mare, spanning an immense 400,000 square kilometers. As images reveal, this gargantuan lake is actually divided into two main parts, separated by a narrow stretch of liquid, quite similar in appearance to Earth's Strait of Gibraltar. Its evocative nickname, The throat of the kraken stems from the belief that, due to intense tidal forces and the sheer size of the lake, the tide within Kraken Mare could fluctuate by as much as 1 meter. This tidal action could potentially create strong currents and even whirlpools within this narrow strait. Kraken Mare is also believed to be quite deep, especially in comparison to Ontario Lacus, though it is not thought to exceed depths of approximately 170 meters. So, we now have a clearer understanding of the lakes and seas on Titan. But what other interesting surface features might this enigmatic world possess? Plenty, actually. Titan's solid surface is considered geologically young, estimated to be as recent as 100 million years old, which implies that its surface must be geologically active, constantly being reshaped and renewed. Some scientists believe the dirty ice crust of Titan is substantially rigid, while others point to evidence suggesting the presence of tectonic activity on the Moon, possibly driven by the immense tidal forces exerted by Saturn. However, the primary factor responsible for Titan's continually renewed surface is most likely the same process that replenishes methane in its atmosphere: cryovolcanism. Now, this is truly fascinating. You know how magma on Earth is incredibly hot, a molten rock that, when it erupts from the ground, eventually cools and freezes to form new land. Well, Titan experiences a strikingly similar phenomenon, but with a crucial difference: its magma is not molten rock, but rather a mixture of water and ammonia. When this icy lava erupts from cryovolcanoes and spills over the land, it too freezes, contributing to the continuous renewal of Titan's surface. Because this blend of water and ammonia is considerably less viscous than terrestrial lava, it flows much further across the landscape. This means that mountains on Titan are generally much flatter and do not reach the towering heights of volcanoes found on Earth. While it is challenging to definitively confirm the existence of specific cryovolcanoes on Titan due to the perpetual obstruction caused by its thick atmosphere, the most likely candidate identified so far is Satrapadura, located in the Moon's southern hemisphere. In images where height has been dramatically exaggerated by a factor of 10, Satrapadura presents a clear dome shape with a central pit approximately 1.7 kilometers deep, the largest such pit known on Titan. The force required for such an eruption would have been absolutely incredible. While Satrapadura does not currently appear to be active, it is under active monitoring by scientists. The fact that Titan's lava is a mixture of water and other minerals means its surface could be aptly compared to dirty ice. Based on how the Huygens probe bounced and wobbled in a specific manner as it landed on Titan, we have a rough idea of what the consistency of the surface might be like. Scientists have likened it to a soft, damp sand. Another intriguing theory suggests it might be similar to snow with a thin crust on top. Imagine walking on frozen, crusted snow. If you tread carefully, you can remain on the solid surface, but if you step too heavily, you will sink quite deeply. Titan's surface is believed to behave in a somewhat similar fashion. Titan's highest mountains manifest in the form of impressive ridge belts, reminiscent of mountain ranges like the Rockies in America. These ridge belts themselves could also be a form of cryovolcanic activity. The largest mountain on Titan, a peak soaring to 337 meters high, can be found within one of these mountain ranges, known as the Mithrim Montes. Interestingly, mountains of this altitude on Titan are thought to be topped with methane snow, adding another peculiar element to this alien landscape. Also found on Titan are numerous gorges, valleys, and vast dune fields. Using sophisticated infrared cameras to penetrate the atmospheric haze and view the surface from space, these large patches of dark terrain are quite prominently visible. Initially, these dark patches were thought to be extensive seas, until the Huygens probe landed on one of these areas, known as Shangri-La. They could certainly have been seas in the distant past, but they are now vast plains of dark mineral deposits, strikingly similar in appearance to the Namib Desert on Earth, where they manifest as immense, windswept dunes in certain locations. Overall, Titan can be compared to Earth in numerous fascinating ways. Scientists even speculate that Titan might offer clues about what early Earth could have been like, albeit in a significantly colder iteration. It is fair to say that Titan is a remarkably interesting world, and I can only express my fervent hope that it will one day receive its own dedicated mission. The Cassini mission performed an incredible service, but it was never solely a Titan orbiter, and its mission, sadly, has now concluded. What I personally would find extraordinarily fascinating is to explore more of its intricate surface, perhaps with a dedicated rover or even an aerial drone, and I sincerely hope it won't be long until a mission to achieve that is approved. Until then, here was everything you could possibly wish to know about Titan. It has now been 3 years since the Cassini mission heroically concluded its epic journey by diving into the atmosphere of Saturn, a final, fiery act of scientific sacrifice. Its mission was, without question, tremendously successful, and in my humble opinion, it stands as one of the greatest and most impactful missions of all time. The colossal volume of data it meticulously collected over its 13 years in orbit around Saturn is still being pored over and analyzed by scientists today, as there remain a multitude of unsolved mysteries pertaining to Saturn and its intricate system of moons. One of Cassini's most impressive and groundbreaking discoveries was the definitive confirmation of the existence of stable, liquid methane lakes and seas on the surface of the solar system's most unusual moon, Titan. However, merely knowing they were there didn't immediately provide answers to the more profound question of how they came into being. But now, after years of dedicated research and analysis, scientists may have finally devised a compelling answer. There are only 2 places in the entire solar system that are known to harbor stable, persistent bodies of liquid on their surfaces, our own planet Earth, and the distant, frigid moon, Titan. However, this shared characteristic does not imply that they are otherwise very similar places. Earth is a rocky planet, characterized by a dense iron core and a silicate mantle. Titan, on the other hand, is an icy world, its crust and mantle primarily composed of water ice, with a vast subsurface ocean of water and ammonia surrounding a rocky core. This fundamental difference means that Earth is considerably denser, and coupled with its larger size, results in a gravitational pull on Earth that is significantly stronger than that on Titan. Both worlds possess dense atmospheres, but due to their stark differences in gravity, Earth's atmosphere clings tightly to the planet, a relatively thin, protective envelope. Titan's atmosphere, although in total slightly more massive than Earth's, stretches hundreds of kilometers above the Moon's surface, expanding outwards due to the weaker gravitational constraint. Their atmospheric compositions are also dramatically different. Earth is situated much closer to the Sun, meaning it is significantly warmer than Titan, a temperature regime that allows for an active water cycle, with liquid water evaporating, forming clouds, and precipitating as rain. Water is perpetually frozen solid on Titan. However, the temperature and pressure conditions on Titan are precisely right for liquid methane to be present on its surface. This means, astonishingly, that Titan experiences a methane cycle, operating in a fashion remarkably similar to Earth's water cycle. Methane clouds have been observed swirling within Titan's atmosphere, and these clouds release liquid methane onto Titan's frigid surface as rain. This process, over immense timescales, actively carves out intricate networks of rivers and channels through the surface ices, which then flow into smaller seas or lakes. Radar data meticulously collected by Cassini, visualized in these detailed images, clearly reveals various riverbeds and valleys, sculpted and cut away by the relentless flow of liquid methane. The most prominent and geologically striking of these flow channels are found around Titan's second largest lake, Ligeia Mare. These ancient channels, evocatively dubbed vid flumina, are particularly special because they appear to be considerably older than any other flow channel observed on the Moon. These canyons boast walls that rise hundreds of meters tall, with incredibly steep slopes. While liquid methane is visible within these canyons today, it is not actively flowing. Instead, they are believed to be drowned river valleys, inundated by the current level of Ligeia Mare, though some high-altitude tributary streams are likely still flowing down into the main canyon. The lakes on Titan can be truly immense. The largest of them, Kraken Mare, is larger than Earth's Caspian Sea, encompassing a staggering area of roughly 400,000 square kilometers. Cassini's radar data suggests that many of these lakes are remarkably shallow, some only a few meters deep. However, some of the larger ones can reach depths exceeding 200 meters. Collectively, the total amount of potential fossil fuels, in the form of hydrocarbons, on Titan is estimated to be over 300 times the proven reserves on Earth, a truly mind-boggling figure. The lakes of Titan are also surprisingly still. Some lakes exhibit ripples no larger than approximately 1 millimeter, meaning their surfaces would appear like perfectly smooth glass or a mirror. This observation initially came as a surprise to scientists who, given Titan's low gravity and dense atmosphere, had expected waves of up to a meter in height to be generated by winds blowing across the surface. This discrepancy could mean several things. It might simply be that there happened to be no wind when Cassini passed over these specific lakes, or perhaps the liquid hydrocarbons are considerably more viscous than initially expected, or, conceivably, the lakes occasionally freeze over, presenting a smooth, solid surface. One other intriguing theory has been proposed that dense aerosols, fine particulate matter suspended in the atmosphere, may settle upon the lake's surface, creating a thin, resilient film that actively prevents waves from forming. The detection of these lakes on Titan would not have been possible without the aid of Cassini's sophisticated radar instrument and an infrared camera designed to peer through Titan's thick, opaque haze. These instruments utilize a process called specular reflection to make their observations. The radar instrument initially detected large, dark patches across the surface, which were subsequently confirmed to be lakes by the infrared camera when sunlight reflected off the liquid surface and directly into Cassini's view, much like observing a glint of light from Earth's oceans from space. Specular reflection, using both the infrared camera and the sun as a light source, became a crucial technique for confirming what the radar instrument was detecting. Interestingly, clouds and the subsequent effects of their methane rain were also detected. In one compelling set of images, a light patch initially indicated dry ground. However, a year later, the same area was imaged again, and this time, darker patches could be clearly seen, indicating a very flat surface, highly likely to be shallow and small lakes formed by recent rainfall. The lakes are not distributed evenly across the Moon's surface. Rather, the vast majority of them are concentrated near the poles. However, the Huygens probe, which was part of the Cassini mission and successfully landed on Titan's surface near the equator, did observe clear flow channels around the equatorial regions as well. So, where are the lakes these channels would flow into? This spatial distribution is thought to be the result of seasonal variations, much like the summer and winter weather patterns on Earth. But on a much grander, at certain points in Titan's extremely long year, 30 Earth years, methane rain would fall in these equatorial parts and pool on the surface. However, these temporary lakes and channels likely evaporate during the rest of the year. As the methane rainfall migrates to the North and South poles, which is precisely what Cassini and Huygens would have observed during their respective missions. Even though Cassini remained in orbit around Saturn for an impressive 13 years, that duration still represents less than 1/2 of a full Saturnian year. Saturn takes a complete 30 Earth years to orbit the Sun once. Therefore, Cassini, despite its longevity, did not capture a complete picture of all the seasonal variations and their profound effects on Titan's hydrology. The lakes likely vary significantly in depth throughout Titan's year, with some potentially drying up completely during certain seasons. There is one other enduring mystery that arose from the Cassini data concerning Titan's lakes, a puzzle that may have recently found a plausible solution. Some of Titan's smaller lakes possess very steep, sharply defined rims that tower significantly above the liquid level. This morphology is quite unusual, as lakes on Earth typically form from erosion processes or the dissolving of soluble bedrock, like limestone, which generally results in shallow, smoothly sloping rims. These are known as karstic lakes. However, this typical terrestrial process does not adequately explain the steep, sided nature of a number of Titan's lakes. Scientists now believe that these peculiar lakes could actually be explosion craters that have since filled up with liquid methane. Models suggest that Titan, in its distant past, was once considerably colder, experiencing nitrogen rain and snow instead of methane precipitation. This liquid nitrogen would have slowly seeped into the Moon's crust, creating vast, subterranean pockets of liquid nitrogen. As the greenhouse gas methane was subsequently pumped into the atmosphere by cryovolcanoes in Titan's past, the world gradually warmed. This warming would have caused the liquid nitrogen, now trapped under the surface, to evaporate and dramatically expand, building immense pressure within these subsurface pockets. Eventually, this pressure would have become so great that the overlying lid of ice literally blew off, leaving behind an explosion crater that subsequently filled with liquid methane. While still a theory, it offers a compelling explanation for these unique features. There is still an enormous amount to be learned from the vast trove of Cassini data. The lakes of Titan, as fascinating as they are, represented only a small aspect of the mission's comprehensive scientific objectives. Scientists will undoubtedly be meticulously piecing together these complex puzzles for many years to come, striving to gain a deeper, more holistic understanding of the entire Saturnian system. I sincerely hope that future space agencies will continue to be as ambitious and as ultimately successful as the Cassini mission. There is still an awful lot to discover out there in the boundless reaches of our cosmos. Now, let's turn our attention to Enceladus, perhaps one of the most intrinsically intriguing objects in our entire solar system. And yet, it is only the sixth largest moon of Saturn, and to the casual observer, appearing in natural light, it looks remarkably unassuming, a small, bright sphere of ice. However, there is profoundly more to Enceladus than meets the eye. It is an incredibly active, icy world, characterized by spectacular jets of water vapor and ice particles continuously pouring out from its southern hemisphere, a phenomenon that has captivated scientists. Thanks to the truly remarkable Cassini spacecraft mission, we have studied and observed Enceladus in exquisite, unprecedented detail, arguably knowing more about its dynamic processes than we do about some of the closer and considerably larger Jovian moons. However, while we have witnessed so much from its outside, it is the interior of this moon that continues to hold so many profound mysteries, secrets locked beneath its icy shell. Let us first establish where Enceladus fits into the intricate tapestry of our solar system. Enceladus is currently the 14th closest moon to Saturn. I specify currently because Saturn's rings harbor numerous tiny moonlets, some of which may or may not be officially classified as moons in the future. However, it is the second closest major moon to Saturn, surpassed only by Mimas, another icy world. This orbital position means that Enceladus traces its path just outside of Saturn's main, prominent rings. Its orbit follows the planes of these rings with remarkable precision, and it completes a single orbit around Saturn in a swift 33 hours. Interestingly, Enceladus is locked in a 2:01 orbital resonance with Dione, Saturn's fourth closest major moon. In simpler terms, this means that Enceladus completes exactly 2 orbits around Saturn in the precise amount of time it takes Dione to complete one. This particular orbital resonance is believed to be the crucial mechanism that prevents Enceladus's orbit from ever becoming perfectly circular. Instead, its orbit remains perpetually elliptical, causing Enceladus to undergo continuous tidal deformation. This is a profoundly significant detail, as these relentless tidal forces generate immense internal heat, effectively warming Enceladus's core and maintaining its internal activity. You see, as far as our observations can tell, Enceladus's surface is predominantly composed of incredibly clean, pure water ice, with remarkably little to no rocky material or other impurities. Because Saturn is situated so far away from the Sun, the outer layer of water on Enceladus has long since frozen solid. Enceladus is, in essence, a frozen ocean world, a giant, pristine ball of water ice.